Generation, or RAG. Today, we're moving beyond simple prompting to learn how to give AI models access to external data. We'll start with a high-level overview of what RAG is and why it's a game changer for reducing hallucinations in LLMs. A clear, conceptual overview of the RAG architecture, explaining the flow from query to retrieval to generation. Now that you understand the what, let's talk about the how. Before an AI can search your documents, those documents must be broken down into manageable pieces. This is called chunking. If chunks are too big, you lose precision. If they're too small, you lose context. Let's look at the core strategies. An in-depth look at different chunking strategies, including fixed size, recursive character, and semantic chunking. Choosing the right chunk size is a balancing act. You need to consider the context window of your LLM and the embedding model you are using. In this next segment, we will explore how to optimize these parameters for better retrieval accuracy. Technical explanation of chunk overlap, sliding windows, and how these impact the retrieval of relevant information. Once your text is chunked, it needs to be converted into numbers that computers can compare. This is where vector embeddings and vector databases come in. Think of it as mapping the meaning of your text into a multidimensional space. Understanding how text chunks are transformed into vectors and stored for efficient similarity searches. The final piece of the puzzle is actually building the pipeline. We'll look at a practical implementation using popular frameworks like LangChain to see how these theories translate into working code. A hands-on coding walkthrough showing how to load a PDF, chunk the text, and query it using an LLM. We've covered a lot today, from the high-level RAG architecture to the granular details of recursive character splitting. Remember, the quality of your RAG system is only as good as the data you feed it, and that starts with smart chunking. Experiment with different sizes and overlaps to find the sweet spot for your specific data. See you in the next lesson.